Welcome back friends. Today we are going to discuss about a new topic in mathematics, the mathematical modeling. The technique of mathematical modeling. Mathematical modeling essentially consists of translating real world problems into mathematical problems, solving the mathematical problems and interpreting these solutions in the language of real world. Look at the figure on the screen. This is expressed figuratively by saying that we catch hold of the real world problem in our teeth, dive into the mathematical ocean, swim there for some time, and we come out to the surface with the solution of real world problem with us. Alternatively, we may say that we soar high into the mathematical atmosphere along with the problem, fly there for some time and come down to the earth with the solution. Classification of mathematical models. Mathematical models may be classified according to the subject matter of the models. Thus, we have mathematical model in physics, mathematical model in chemistry, mathematical model in biology, mathematical model in medicine, mathematical model in economics and so on. We have similarly mathematical modeling of transportation, of urban and regional planning, of pollution, of environment, of oceanography, of blood flows, of genetics, of water resource, of optimal utilization of exhaustible and renewable resources, of political systems, of land distribution, of linguistics and so on. In fact, every branch of knowledge has two aspects, one of which is theoretical, mathematical, statistical and computer based, and the other of which is empirical, experimental and observational. Mathematical modeling is essential to the first of these two aspects. Some characteristic of mathematical models. First one, realism of models. We want a mathematical model as realistic as possible and to represent a reality as closely as possible. Second, relative precision of models. Different models differ in their precision and their agreement with observations. Third, robustness of models. A mathematical model is said to be robust if small changes in the parameters lead to small changes in the behavior of model. The decision is made by using sensitivity analysis for the models. Fourth one, self-consistency of models. A mathematical model involves equations and these must be consistent. For example, a model cannot have both x plus y greater than a and x plus y less than a. Fifth, a model may be good, adequate, similar to reality for one purpose and not for another. Thus, we may need different models for explaining different aspects of the same situation or even for different ranges of the variables. Sixth, modeling forces us to think clearly. Before making a mathematical model, one has to be clear about the structure and essentials of the situation. Seventh, modeling in terms of modules. One may think of models for small modules and by combining them in different ways, one may get models for a large number of systems. Eighth, state variables and relations. For making a mathematical model, one has first to identify the state variables and then specify the relation between them. Ninth, estimation of parameters. Every model contains some parameters and these have to be estimated. The model must itself suggest experiments or observations and the method of calculation of these parameters. Limitation of mathematical modeling. There are thousands of mathematical models which have been successfully developed and applied to get insight into tens of thousands of situations. In fact, mathematical physics, mathematical economics, operations research, biomathematics, etc. are almost synonymous with mathematical modeling. However, there are still an equally large or even a larger number of situations which have not yet been mathematically modeled, either because the situations are sufficiently complex or because mathematical models formed are mathematically intractable. Successful guidelines are not available for choosing the number of parameters and of estimating the values for these parameters. Now, let us consider mathematical modeling through differential equations. Mathematical modeling through differential equations. Mathematical modeling in terms of differential equation arises when the situation modeled involves some continuous variables varying with respect to some other continuous variable, and we have some reasonable hypothesis about the rate of change of dependent variables with respect to independent variables. When we have one dependent variable x, say population size, depending on one independent variable, say time t, we get a mathematical model in terms of an ordinary differential equation of the first order if the hypothesis is about the rate of change dx by dt. The model will be in terms of an ordinary differential equation of the second order if the hypothesis involves the rate of change of dx by dt. If there is one dependent continuous variable, say velocity of fluid u, and a number of independent continuous variables, say space coordinates x, y, z and time t, we get a mathematical model in terms of a partial differential equation. Using non-physical laws to construct mathematical model is one of the most widely used methods in the hard science and engineering. For example, a block of mass m is dropped from a height h above the ground. What is the motion of the block? The physics of motion is known to be governed by Newton's law, which states that the rate of change of momentum of an object at time t is equal to the net force on the object at time t. This physical law will play a central role in the solution of this problem. The verbal description would be as follows. Given the mass of a block and the height above the ground from which it is dropped, the velocity of the block and position of the block above the ground are to be found as functions of elapsed time since the block was dropped. With this verbal description in hand, the non-variables are the mass m of the block and the height h from which it is dropped. The unknown variables are the velocity function vt giving the downward velocity of the block at time t and altitude function at giving the height of the block above the ground at time t. Having made these observations, re-examining the verbal description shows that v of 0 is equal to 0 is known to, and the convention has been introduced that time t is equal to 0 corresponds to the time at which the block is dropped. Also, A of 0 is equal to h. We assume that air resistance is negligible and that the gravitational force acting on the block is constant, independent of the height of the block above the ground. The mass of the block is also assumed to be constant. In this case, the net force acting on the block is the gravitational force mg, where g is the gravitational constant, that is g is equal to 9.8 meters per second. The moment of the block at time t is m into v of t by definition of momentum. Applying Newton's law then gives m into v dash t is equal to mg as one equation relating the variables. The definition of velocity gives a dash t is equal to minus v t as another relation. The mathematical statement of the original problem is as follows. Given constant m greater than 0 and h greater than 0 and functions v of t and a of t satisfying m into v dash of t is equal to mg with v of 0 is equal to 0 and a dash of t is equal to minus v t with a of 0 is equal to h. Find the functions v of t and a of t for t greater than or equal to 0. Next, linear growth and decay models. Population growth models. Let x of t be the population size at time t and let b and d be birth and death rates, that is the number of individuals born or dying per individual per unit time. Then in time interval t, t plus delta t, the number of births and deaths would be b into x into delta t plus 0 of delta t and dx delta t plus 0 of delta t, where 0 of delta t is an infinitesimally small which approaches 0 as delta t approaches 0. So, that x into t plus delta t minus x of t is equal to b into x of t minus d into x of t into delta t plus 0 of delta t. So, that dividing by delta t and proceeding to the limit as delta t tends to 0, we get dx by dt is equal to b minus d all into x, which is equal to ax. Say, integrating the second equation, we get x of t is equal to x of 0 into exponential of at. So, that the population grows exponentially if a greater than 0, decays exponentially if a less than 0 and remains constant if a is equal to 0. This is given in the following figure. If a greater than 0, the population will become double its present size at time capital T, where 2 into x of 0 is equal to x of 0 into exponential at, or exponential at is equal to 2, that is t is equal to 1 by a log 2, which is equal to 0.693141118 a inverse. T is called the doubling period of the population, and it may be noted that this doubling period is independent of x of 0. It depends only on a and is such that greater the value of a, that is greater the difference between birth and death rates, the smaller is the doubling period. When half of x 0 is equal to x of 0 exponential at, or exponential at is equal to half, or t is equal to half of log 1 by 2, which is equal to 0.693141118 a inverse. It may be noted that t is also independent of x 0, and since a less than 0, t greater than 0. T may be called the half life or period of the population, and it decreases as the excess of death rate over birth rate increases. Next, non-linear growth and decay models. Logistic law of population growth. As population increases due to overcrowding and limitation of resources, the birth rate B decreases and death rate D increases with the population size x. The simplest assumption is to take B is equal to B1 minus B2 into x and D is equal to D1 plus D2 into x, where B1, B2, D1, D2 greater than 0. So, that second equation becomes dx by dt is equal to B1 minus D1 whole minus B2 plus D2 into x, which is equal to x into a minus bx, where a greater than 0, b greater than 0. Integrating the above equation, we get xt by a minus b of xt, which is equal to x of 0 by a minus b into x of 0 whole into e raised to at. Equations 7 and 8 show that x of 0 less than a by b implies x of t less than a by b, which implies dx by dt greater than 0. This implies that x t is a monotonic increasing function of t which approaches a by b as t tends to infinity. Similarly, x of 0 greater than a by b implies x of t greater than a by b, which implies dx by dt less than 0. That is, x of t is a monotonic function of t which approaches a by b as t tends to infinity. Now, from 7th equation, d square x by dt square is equal to a minus 2 into bx. So that d square x by dt square is greater than 0 or equal to 0 or less than 0 according as x is greater than a by 2b or x is equal to a by 2b or x is less than a by 2b. Thus, in case the growth curve is convex, if x less than a by 2b and it has a point of inflection at x equal to a by 2b. Thus, the graph of x t against t is as given in the figure. If x 0 less than a by 2b, x of t increases at an increasing rate till x of t reaches a by 2b and then it increases at a decreasing rate and approaches a by b as t tends to infinity. If a by 2 into a b is less than x of 0 which is less than a by b, then x of t increases at a decreasing rate and approaches a by b as t tends to infinity. And if x of 0 is equal to a by b, x of t is always equal to a by b. If x of 0 greater than a by b, x of t decreases at a decreasing absolute rate and approaches a by b as t tends to infinity. Next, spread of technological innovations and infectious diseases. Let n of t be the number of companies which have adopted a technological innovation till time t, then the rate of change of the number of these companies depends both on the number of companies which have adopted this innovation and on the number of those which have not yet adopted it. So that if R is a total number of companies in the region, dn by dt is equal to k into n whole into r minus n, which is the logistic law and shows that ultimate all companies will adopt this innovation. Similarly, if n of t is the number of infected persons, the rate at which the number of infected and susceptible person, as such we again get dn by dt is equal to k into n whole into r minus n, where r is the total number of persons in the system. It may be noted that in both the examples, while n of t is essentially an integer valued variable, we have treated it as a continuous variable. This can be regarded as an idealization of the situation or as an approximation to reality. Next, age structured population models. Let x1 of t, x2 of t, etc., xp of t be the population of the p pre-reproductive age groups. Let x p plus 1 of t, etc., x p plus q of t be the population of the q pre-reproductive age groups and let x p plus q plus 1 of t, etc., x p plus q plus r of t be the population of the r post reproductive age groups. Let b p plus 1, b p plus 2, etc., b p plus q be the birth rates in the q reproductive age groups. Let di be the death rates in the ith age group for I is equal to 1, 2, etc., p plus q plus r, and let mj be the rate of migration from the jth age group to the j plus 1th age group for j is equal to 1, 2, 3, etc., p plus q plus r minus 1. Then we get the system of differential equations as dx1 by dt is equal to b p plus 1 x p plus 1 plus b p plus q x p plus q minus d1 plus m1 into x1, dx2 by dt is equal to m1 x1 minus d2 plus m2 x2, etc. dxn by dt is equal to mn minus 1 x n minus 1 minus dn xn, where n is equal to p plus q plus r. Or this can be expressed in the matrix form with first entry d1 plus m1, second entry 0 and so on. That is d by dt of x1t, x2t, etc. xnt is equal to d1 plus m1 0 etc. b plus 1 etc. b plus q etc. so on into x1t, x2t etc. xnt, or dx by dt is equal to a into x of t, where A is a matrix all of whose diagonal elements are negative, all of whose main sub-diagonal elements are positive, q other elements of the first row are positive and all other elements are 0. Positive and all other elements are 0. Equation 12 has the solution x of t is equal to exponential a t into x of 0. The need for mathematical modeling through difference equations. Some simple models. We need difference equation models when either the independent variable is discrete or it is mathematically convenient to treat it as a discrete variable. Thus, in genetics, the genetic characteristics change from generation to generation and the variable representing a generation is a discrete variable. In population dynamics, we consider the changes in population from one age group to another and the variable representing the age group is a discrete variable. For mathematical modeling through differential equations, we give an increment delta x to the independent variable x, find the change delta y in y and let delta x tends to 0 to get differential equations. In most cases, we cannot justify the limiting process rigorously. Even if the limiting process can be justified, for example, when the independent variable is time, the resulting differential equation may not be solvable analytically. We then solve it numerically and for this purpose, we again replace the differential equation by a system of difference equations. Numerical methods of solving differential equations essentially mean solving difference equations. Example, the classical example in which a difference equation arises is the case of the Fibonacci sequence 1, 1, 2, 3, 5, etc. Fibonacci postulated that each pair of rabbits that is at least 2 months old will produce another pair of rabbits each month. Denote by Rn the number of pairs of rabbits at the beginning of nth month. If there is one pair of newborn rabbits at the beginning of the first month, R1 is equal to 1. By hypothesis, R2 is equal to 1 as well, since the rabbit must be 2 months old to reproduce. Then R3 is equal to 2 and generally Rn is equal to Rn minus 1 plus Rn minus 2 under the assumption that rabbits never die. Mathematical modeling through difference equations in population dynamics and genetics. Nonlinear difference equations model for population growth. Nonlinear difference equations. Let xt be the population at time t and let births and deaths in time interval t plus 1 be proportional to xt. Then the population xt plus 1 at time t plus 1 is given by xt plus 1 is equal to xt plus b into xt minus d into xt, which is equal to xt into 1 plus a. This has the solution xt is equal to x0 into 1 plus a whole raised to t, so that the population increases or decreases exponentially according as a greater than 0 or a less than 0. We now consider the generalization when births and deaths b and d per unit population depend linearly on xt, so that xt plus 1 is equal to xt plus b naught minus b 1 into xt whole into xt minus d naught plus d 1 into x 1 whole into x 1, which is equal to m into x t minus r into x t square, which is equal to m into x t whole into 1 minus r by m x t. This is the simplest nonlinear generalization of equation 15 and gives the discrete version of the logistic law of population growth. However, this model shows many new features not present in the continuous version of the logistic model. Let r into x t by m is equal to y t. Then equation 16 becomes y t plus 1 is equal to m into y t whole into 1 minus y t. Now, let us summarize what we have studied in this session. Today, we have discussed about mathematical modeling. Two different techniques, differential equations and difference equations, are used to study mathematical modeling. In this case, we concentrated on different population models and spread of technological innovations. Here are some exercise problems based on the topics discussed. First one, in mass block example, why does the minus sign enter into the expression for a dash of t? Second, in the rabbit example, the only equilibrium solution is the 0 solution, that is R n is equal to 0 for all n. It is also clear from the equation R n minus 1 is equal to R n minus 2 that 0 is an unstable equilibrium. Once the value of R differs from 0, the subsequent values of R will diverge to infinity. Explain why the subsequent values of R will diverge. Third, the mass mt of a person at time t is affected by caloric intake of the person as well as the rate at which calories are burned by the metabolism and exercise. The person in question consumes food which provides 1600 calories of energy per day. Basic metabolic function uses 900 calories per day. Exercise consumes 20 calories per day per unit of the body mass. Unused calories are stored by the body as fat. Calories needed by the body in excess of those obtained through food are obtained from the fat store. Energy is stored in the fat at the rate of 10,000 calories per kilogram of fat. Conversion of energy to and from fat is assumed to be perfectly efficient. According to this information, what is m of t? What additional assumption, if any, have you made? What is the equilibrium value of the mass for the person in question? Fourth one, labor and management are in a dispute over wages. Management initial wages offer was m0 rupees per hour, while the labor negotiators wanted L0 rupees per hour. It is reasonable to suppose that each offer will be updated by increasing or decreasing the previous offer by a fraction of the current difference in positions. Investigate the behavior of such a model. Will there be a wage agreement? If so, what will the amount of wages be? Fifth one, analyze graphically the dynamics of the following equations. In each case, plot dx by dt versus x, find all equilibrium, determine their stability and sketch the qualitative shape of x of t versus t for various starting values as we did for the logistic equation in lecture. A, dx by dt is equal to 1 minus x2, consider also x less than 0. B, dx by dt is equal to x into x minus 0.5 into 2 minus x, consider only x greater than or equal to 0. I can suggest you some books for further reading. First one, An Introduction to Mathematical Modeling by Edward A. Benter, Wiley InterScience publication. Second, Concepts of Mathematical Modeling, Walter J. Mayer, Dover publications. Third, Mathematical Modeling, Classroom Notes in Applied Mathematics, edited by Murray Clamkin, Siam publications. Fourth, Differential Equation Models, Volume 1, edited by Martin Brown, C. S. Coleman and D. A. Drew. Fifth one, A Concrete Approach to Mathematical Modeling by Mike Masterton Gibbons, Wiley InterScience publication. Thank you for watching this program. We will continue with our discussion on mathematical modeling in the next session. Till then, bye.